So, welcome to a new chapter and a new set of lectures in which we talk about the beautiful concept of electrostatic potential and certain gadgets based on the concept of potential energy and the storage of potential energy through capacitors. Okay. Now, I will go slow. I'll go slow. So please follow me. Recall. Let's go back to our exercises in the force and the potential energy and the kinetic energy and the kind of forces that we work with. What done against? What is this force? F is equal to minus kx. This is the force for springs, the system of springs. What does that mean? It is the system of elasticity. What does that mean? Elasticity comes from the togetherness of the atoms and molecules, okay, and that means we are talking about the forces which are manifest in what we call the electromagnetic forces. Okay. F is equal to minus kx, where k is the force constant, is the spring constant, etc. And the negative sign indicates that x and f, they are in opposite directions, right? That means our F is a kind of a restoring force which tries to bring the disturbed body towards its equilibrium condition. Then we have had a long discussion about F is equal to minus capital G M upon R square or M1 M2 upon R square, which is the gravitational attraction. It's only because of the attractive nature that I'm putting minus sign over here. I gave you the concept of kinetic energy, half mv square. We had the concept of potential energy, which is half kx square, okay, and the potential energy, the concept we have mgh, etc. This we all know. We also know that these two forces were considered to be conservative forces, and particularly in this case, because there is the inverse square law dependence, therefore these set of forces are all conservative forces. What does that mean? That it means that the total of the kinetic energy and the potential energy of a system in isolation, when the force is working on it, then that is constant, that does not change, that is conserved. Okay? So please recall all these things. Okay? Now, F is equal to 1 upon 4 pi epsilon or epsilon naught q1 q2 upon r squared, this is Coulombian force, where epsilon r is a number normally equal to or greater than 1, and epsilon r into epsilon naught is the epsilon of the medium in which the Coulombian force is working. Okay, so I can say that epsilon is equal to epsilon r upon epsilon naught. So whatever is the unit of epsilon naught, the same is the unit of epsilon r, and this is epsilon r just is a ratio of the two, and therefore its unit is, this is dimensionless. Epsilon r is equal to epsilon, the medium, for example water, and the medium which is called air or vacuum. Okay, it doesn't matter. Just like that, I introduced it to you so that you are okay using this. Now, in this instance, in the case of the gravitational force, I have the universal gravitational constant of the system. But in the case of this Coulombian force, we have 1 upon 4 pi epsilon or epsilon naught as the constant. They have similarity, okay, but they are not akin of each other. They are not cousins. Okay. They are in different circumstances. Okay. So these are certain things that I want you to know. Now let us take a system where I have a charge capital Q held at the origin. When I say held, and you ask me a question, how come? Then I say, I don't know. Bhagwan jane. Wallah alam bisawab. This imagination. So it is held here. Okay? It is situated here at the origin. And then let us take 2 points R and P which are on the line joining the origin. And here I have just shown to you a charge which is plus Q, which is a test charge. Okay? Normally taken as very, very small, and so small, this positive charge, that there cannot be any change in the charge configuration. What is this Q? Q can be a single charge like is shown over here, or Q could be the cumulative effect of so many charges distributed in space, but we say that the net effect is as if a charge plus capital Q were placed here on the origin of the coordinate system. Okay, so suppose my test charge is here. So what will happen? Mr. plus Q, now there is nothing. We are not there. Okay? Only our imagination is there. So what will happen? This Mr. Q, small q, will experience a field in this direction. Okay. So there will be a force that will be Fe, which is working like this. I have shown to you that the force and the electric field at this point, any point here, they are in the same direction, because this is plus q and this is also plus q. Can take them to minus q and minus q, no problem. Anyway, it's good that plus q are taking, so we are not confused. Okay. Our confusion is ironed. Okay. So my charge is here and there is a force in this direction. Now, if we want to move this charge towards the origin, okay, we will have to push this charge at least with an equal and opposite force, which I described here as F external. Minimum, equal and opposite. But we'll take it to be equal and opposite. And push this. Look here. If there were all by itself a force in this direction, then this charge, which may also have a mass too, okay? This should have a mass because it's a matter particle. So that will be pushed in this direction. By whom? By the net force. Has a mass, there is a force, so Who comes in between? Newton's second law. F is equal to m into a, or a into m, where a is our friend acceleration. Okay. So it will be accelerated all by itself if there is a net force in this direction, but there is no net force in this direction. So I have written that q is greater than 0, q is greater than 0, q tends to 0, so that there is no change in the charge configuration. Okay. And if at all, then those charges are held by an unknown force, which we imagine to be there. Because without that imagination, our work is not to be translated into ideas. Okay. So the movement of this charge from here towards P, we want to start with R and we want to end up at the point P. And we say that there is no acceleration. That means this charge is moved from R to P or infinitesimally small force, which is almost equal to 0. This kind of movement we have defined as quasi-static, quasi-static, and even some people they call it quasi-static. It doesn't matter. You can check for yourself. So there is a translation from the point R to the point P, okay, without any acceleration. And the two forces, external and Fe, they sum up to equal to 0, so that one is equal to the other with minus sign. Okay. Now let's see. The work done by the external force, which you have just imagined, which you have just introduced, is equal to minus 1 times the work done by the force due to the electric field that is there and working at cross Q. Okay. Now, this fellow, the work done by the external force, this is stored in the form of potential energy of the charge small q, in the form of the potential energy of charge q. So let us see. Mathematically, WRP is equal to, from R to P, F external dot dr. Okay. Equivalently, because of this kind of relation, this is equal to minus times, opposite. Minus times R to P F E dot dr. Okay. And you know that F dot dr, F dot dz, F dot dy, F dot dx, this is all work done. Okay. What is it? Work done? Is it a vector or a scalar? Scalar, 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 because this is the dot. Okay. So now, what I said here, this is stored as potential energy. Stored as potential energy. And the symbol we use for the potential energy is U. U is the symbol which we use as the potential energy. Now, there is nothing like absolute potential energy. Okay? We don't deal in absolute potential energy. Even when I have a mass here, I have a mass here, okay? I have a mass here. It has got a certain potential energy, some mgh, okay? And if I want to take it here, okay, there is another potential energy of mgh dash. Now this h can be measured from here, h can be measured from the floor, h can be even measured with respect to this, And then the values that we have, they differ under different conditions. But the work done when the object is taken from here to here, in the case of this gravitational field, small g, which is taken to be constant in this context, okay, that is the difference of the two potential energies. Okay, so we write that delta U is equal to UP minus UR. It can have a value. I can write this as UP plus Delhi. Okay, and I can take this as UR plus Delhi, right? Where D is a constant. D can be any constant, alpha, beta, gamma, delta, A, B, C, D, ka, kha, ga, ga, alif, ba, ta, sa, anything. But this is added to the value over here. But you can see, my friend, that if I have a certain thing like that, then D and D will cancel out. Whether positive or negative or zero or whatever, they cancel out. So we are again left with, what is that? UP minus UR, which is equal to what? RT. So this is the change in the potential energy of the system. So what we are, and I told you that I'll go very slow. So I'm going slow again. What is important? Potential energy is important. Potential energy is important. But what's important is the difference of the potential energies between 2 points. Now, next we define what is potential and see that there also it is the difference of the potential. And so you must have, the word potential difference, and the set of words, and you also know the same thing as voltage from your class 9, 10. Okay, and you know that the voltage is how many volts here? 220, 230, like that, 110 in some of the countries for the alternating current system that we have in our home power supply. So from R to P, we did write the work done from R to P is equal to UP plus some D minus UR plus same D. Alpha, beta, gamma, anything you can take. This is a constant. So this will cancel out with this, and we got UP minus UR. Okay. So we can now write, instead of R, we go to infinity. Okay, infinite distance apart. So now we define W infinity to P as UP minus U infinity. And it's very convenient for us to take the value of U at infinity to be equal to 0. Then this becomes equal to UP. Okay, the potential energy at the point P under the influence of the charge capital Q that we had taken here. Well, now let's have a definition, and the definition is that the potential energy at the point P is the work done by F external, the external force, which is equal to minus times F due to the electric field in bringing a test charge Q from infinity to capital P. Okay, and I must tell you right now that there is a kind of path independence, and that the movement or translation is quasi-static, which is very slow process, but our imagination can go down to very slow to very fast. Okay. Well, now we define the electrostatic potential, for which the unit has been taken as capital V, and the representation is with letter capital V, and the unit is volts. I'll not talk about the unit just now, but this is in the name of Mr. Volta, who was associated with a voltaic cell, and to honor him, this very beautiful concept of potential, etc., that is expressed in terms of volts in his name. Okay. Now, here we define this potential is the work done divided by the test charge Q. Sometimes people say that this is the work done per unit charge. I don't subscribe to you, because I am always very afraid of the unit charge. Unit charge could be as big as could be accommodated only in a football field and 100 meters on the top of the earth. Well, so this now we can define from here that work done in bringing that charge Q from infinity to the point P under the consideration that everything is positive, that is defined as Vp. Okay. And the definition which emerges is in the text is the work done in bringing a charge from infinity to the point P per unit positive charge. Okay. So per unit positive charge does not mean that the positive charge of unit value, that is 1 coulomb, is being brought from infinity to that point. No. So the other thing is that if we move from R to P, now we are just choosing, forgetting about that capital Q and this and that and the configuration of charges because of which electric fields exist, and we move from point R to point P. There is a possibility that we can take path 1, your choice, give it number 2, give this number 3, and give this number 8, no problem. The numbering need not be in sequence. Okay. So 1, 2, 3, 8, these are the various paths through which quasi-statically we move from the point R to the point P. Okay. What we find is that the value of Vp and value of Vr, okay, and any dynamic charge that you want to bring from here to here, that work done is path independent. What it is? It is path independent, right? And therefore, what we are talking about right now are set of conservative forces. All definition of conservative forces, they subscribe to this concept that from one point to another point there is path independence. I have been slow. I had to be slow. And I suggest that this lecture should be heard, should be listened to, should be studied at least 2 times. Okay. Now next in offing is to find an expression for the potential, electric potential due to a point charge, due to an electric dipole, due to a system of charges, and talk about what are known as equipotential surfaces. Okay, and there I will tell you a relation that exists between the electric field and the potential. Okay, and there is a gradient kind of thing that I will introduce to you. I'm just taking the name just in case you are lured to learn about that and come back to the next class loaded with some information, and hope it is not a lot of confusion, but any confusion that you have is most welcome. Next we go to the potential energy of a system of charges, etc., etc., etc. in this chapter, and go on to learn about the capacitors. Thank you very much. Okay. See you.